Wow, thank you, everyone. Thank you for having me. I hope this sound is good. I've never spoken into the mic yet on this stage, so let's figure it out. Cool, yeah, we're going to talk thinking like a data scientist. First, I'm going to credentialize myself a little bit with changing this slide to About Me. I am a ThoughtWorks consultant. My official job title is Data Witch, because we don't really have job titles like that. But yeah, so, oh, I don't like this. Yeah, I have graduate research in economics. Actually, it's experimental economics. And to drill into that a little bit more, it was the subfield of neuroeconomics. So neuroeconomics is this practice where we take human subjects and we put them in a laboratory and we piss them off in some way. We make them hungry and then we put food in front of them, or sometimes we just literally give them hormones and we're looking at the brain scans and or just the straight up behaviors of what these people are doing. Sometimes we make them hold their arms out for a really long time and then test their wherewithal in making hard decisions or something like that. So my background, I cut my teeth in predicting human behavior when I make them uncomfortable in a laboratory. I flunked out after 3 years. It's fine. You don't need a degree to be a data scientist. Nowadays, I've been doing it for, I don't know, 6 or 8 or I don't know how many years, but a while. I'm a generalist in the data space, I'd call myself. These days, I write Clojure for work and for play, and I'm really enjoying that. So if you don't know, the field of data science is having, oh no, I don't want that yet. The field of data science is having an identity crisis. If you ask a data scientist, or anybody really, what is a data scientist and what is data science? Or where does the border stop? When are you an analyst? When are you just doing ETL? When are you actually a data engineer? None of us know the answers to these questions. The people who are doing it don't know the answers. The people who are paying people to do it also don't know the answers. But we can come to consensus about a couple things that data scientists generally do. One, data scientists do predictions, categorizations, clustering. We also write software. And we do visualizations. We communicate the findings of our data to ourselves, to our future selves, who definitely won't understand what past self was thinking, to our stakeholders, to our customers. Visualizations are an integral part of being able to communicate your data. Also, if you don't know this, this is a thing that also happens. I think this is a general problem for specialists in lots of different areas in computer science, that oh, you can do this really cool thing. I'm going to hire 10 of you, throw you in a room, give you lots of money, and you're going to somehow solve my business problem and make me money. And this is a really unfortunate thing that a lot of data scientists experience, where we find a really cool lab that has a lot of cool problems to solve, and we're given no access to different people inside of the company, no interface with the customers, no way to build a network that we can actually do something meaningful inside of the company. And so what happens is people pay data scientists to magically fix their business problem without actually giving the data scientists access to the tools they need. So to recap, we have code, we have models, we have visualizations, we have some magical mojo, and this brings us business value. This is how a data scientist is useful. I'm going to give you some controversial opinions about data scientists that I think, and we at ThoughtWorks think are ways to solve this magical mojo problem that I've talked about. First of all, data scientists should be good software developers, fundamentally, and API developers who can make endpoints where their data can be accessible and queryable. They should be good at writing infrastructure as code and doing continuous delivery. Data scientists should be able to speak the language of the business. They should be talking with stakeholders about key performance indices. They should be able to talk about customer value and what brings meaning to the company. And if you're not doing these things, then I would argue that maybe you're living in a silo. Maybe you're not being that useful as a data scientist. It's not that you're a bad data scientist. You could be the best data scientist in the world, but if you don't know how to integrate with the other people in your company, then I would say, what are you actually doing at this company? Probably cool science, maybe not making your boss that happy. But we're here to talk about how data scientists actually think, not just what data scientists do. So I'm going to answer this question with a story about cholera. Yay. Cholera, I can't believe I made these slides, and I can't believe people invite me to give this talk. But so cholera is a deadly bacteria that can kill within hours. Basically, all the water in your body just tries to get out as fast as possible. It's extremely not comfortable, and it's not pretty at all. It's just dehydration is what kills you. But the cure for cholera costs about 10 cents. It's basically salty sugar water. And this was discovered not too long ago, but it's still a problem today, even though we have the cure. This also used to be a problem. I mean, it was a problem everywhere in the world, mostly wherever there is, I'm not going to spoil it yet, but we're going to talk about London. But I would highlight that this is also still a problem today in places in the world. So the cause of cholera was not known. The way that it is spread and transmitted was not known in, say, 1854, the time period that I want to talk about. What they thought it was this thing called miasma. This is literally bad air. This is the idea that bad smells cause disease. This is why you see these masks the doctors wear, these bird masks. What they would do is they'd put rose petals or vinegar on a sponge or something that would either cancel out or cover up the bad smell. They thought that by providing a different smell or fighting that smell, they would actually prevent the disease. And there was bad smells in London. In the 1800s, there was one summer that they've remembered in the history books as the Great Stink. The Thames was just really smelly, so smelly they gave it an epithet. Human waste was just usually, sewage was like a pretty new concept for people. So human waste was often just dumped into these pools, open air, like the smell going everywhere. People would die or drown in those. Or if they were closed, they would build up these methane gases and then explode and also kill people. Waste from houses, slaughterhouses, industrial plants, all this waste was just being dumped into the Thames and generally gunking stuff up. This is a picture, a personification of the Thames. He's this kind of Donald Trump-looking guy handing over these deadly diseases to the people of London. And this one on the far right is a depiction of cholera. Charles Dickens used too many words, like he always does, to describe that it smelled bad. So maybe you could imagine that there was some sort of model that the scientists and the priests and the people of the mid-1800s had about how this disease worked. What different inputs would cause some output of contracting cholera or dying. And this is what I imagine it looked like. I imagine there was we have a function of bad air plus sins, I guess. Maybe you have too much blood, or you don't have enough mucus, or your humors aren't balanced out correctly. And then some other old-fashioned beliefs. And we have our error term, and that predicts whether or not you contract cholera. Now we're going to start talking about one specific outbreak of cholera in 1854. There was this guy named John Snow. I tried to Google him, and all I could find was pictures of this guy. Maybe that's the historical John Snow. I don't know what this is about. But I do know that what he did was he wanted to look at the data. And he also, as a scientist, because thinking like a data scientist is actually just thinking like a scientist, he wrote down his formal hypothesis. He said, I have a null hypothesis. The null hypothesis in the 1850s is this bad air theory. And I also know as a scientist, says John Snow with his wolf, that my null hypothesis is usually that things are either normally distributed or uniformly distributed. This is not the case for everything. There's lots of things that have other distributions in nature and in social phenomena. But generally, things are going to be normally distributed or uniformly distributed, or they're going to be distributed differently because of some external influence. To give you a more tangible example of this, we're going to look at this Galton board. Galton, I don't know how to say his name. But basically, so we're taking all these little baby marbles, and we're dropping them down. Okay, now we're resetting it. We drop them down onto these pegs. And every time a ball hits a peg, there's a uniform probability of a ball bouncing to the left or to the right. It's a natural phenomenon that happens with a uniform probability, A or B. This is like flipping the chance of getting heads when you flip a coin. But interestingly, when you combine many uniform probable events over time, you end up getting a normal distribution because of the central limit theorem. So this is why, I'll go back for a second, this is why we have many uniform, like every time it hits a peg, we add one more event to the uniform, the count of uniform distribution events, and they tend to form this normal curve that we see. So this is why things are either uniform or normal, and this is an example of the central limit theorem. So let's formally write out our hypothesis in 1854. People living in equally odorous parts of town, if we control for the smelliness, will have uniform likelihood of contracting cholera. And so John Snow says, what if we just talked to the poor people? What if we figured out what their lived experiences were? And this was a pretty new concept for doctors to go and do surveys of the people that they were trying to cure. So what did John Snow discover? He met some workers who worked at a brewery. They made beer, and they were given a ration of beer every day. And I'll go back for a second. So the people who worked at the brewery, they survived. The people, and at the same time, their families were among these people who had who were much more affected by cholera. Many of their families died, while none of the people who worked at the brewery contracted cholera. There were children of specific families who all died, but nobody in their family died. And there was this one lady, she's like one of my favorite people in history. She, a complete outlier. She lived in a non-stinky part of London, I guess far away from the Thames. Maybe they had good sewage out there. She died. She was the only one in her neighborhood, or the only person in her social circle, or whatever. She was totally alone in her contracting cholera and dying. So we have this old hypothesis, the null hypothesis. And John Snow, after collecting this data, was able to come up with his alternative hypothesis, that it's not people who are exposed to bad airs, it's people who drink water that has been contaminated with human waste, that is also contaminated with the cholera virus that produces people who have uniform likelihoods of contracting cholera. So it's not the bad airs. The alternative hypothesis is that's drinking contaminated poo water. So, as it turns out, the workers at this brewery drank mostly beer. And the water had been boiled. Although it came from a place that may have been contaminated with cholera, it had been sanitized. The children who died, they went to school near one infected well that was pulling water up from a nearby sewer, from a well that had been leaked into by a nearby sewer, and they were basically drinking this human waste. It was the same well that this woman loved the flavor of the water. She sent somebody to go get water from that well every day because it was her favorite well water. And so this is how a person nowhere near this one well was able to contract cholera. And this, when Jon Snow discovered that he had already been suspect of this well. The children are dying, the people whose family, the people who work at the brewery, their families live near this well. But then when this one lady who just loved the taste of that contaminated poo water, when he found out that she loved that well, then he organized a group of people, and they went and they took the handle off of the pump so that people couldn't get water out of that well. Here's a map. And this was also integral to Jon Snow's ability to identify what was the cause of the cholera outbreak on Broad Street. No surprise, the father of what's called exploratory data analysis suggests that you visualize the things that you're working with. And this was a map that Jon Snow had made by hand. Each of these, this big black thing you see kind of south of the pump, each of those, there's little tick marks to denote people who contracted cholera. And if you were to zoom out on this map and see the one outlier, this one lady nowhere near the pump, that was really the thing that tipped him off, or gave him the idea to go talk to that lady's family. So as a fun fact, when the word statistics was invented, it was invented because we already were starting to do this math or collect this data about people, about human beings who are affected by the daily goings-on of society. Statistics is directly related to the idea of the state or the idea of a community. A less fun fact is about 40 years after the discovery of the cause and spread of cholera, we already have evidence of states choosing to forego the well-being of those people within their state in order to support their economic activities or the needs of the politicians or business people in their countries or towns. So Hamburg had a problem. They had a cholera outbreak. They knew the technology that was there to prevent it. But they chose not to. They chose to allow themselves to continue prioritizing their being a port city that needs to do all these exports, and to hell with those poor people. They're not that important. They're not impacting business too bad, so we're just going to let them die off. Maybe this type of behavior is related to why people riot when there's cholera outbreaks. I'm not going to go too far to hypothesize that. So what are the lessons here? Data is good. More data is better. And to visualize your data. The map was truly integral to the discovery of the cause of cholera. And what I think is one of the most pressing issues in data science today is, do we really need machine learning for this? We didn't even need a linear regression to solve this problem. We were able to examine the data, come up with a model, and prove our hypothesis. So Jon Snow was able to, exactly that. Have a nice model in his mind that he wanted to test, gather more data, put it against the model, see if it worked, and validate it. In modern times, we call this data exploration. This is what you do when you don't have access to your users or the things that are producing your data points, but you already have some data. You can visualize it, you can do descriptive statistics, you can somehow ask your data questions, you can listen to the people, and explore different hypotheses that you might have. So let's talk about models. As I hinted at before, a model is a function that takes some inputs and makes a prediction. Ooh, let's try this cool functionality. So, does it work? It works. Oh, that's no fun. But, okay, I was trying to point to this green E. This is our error term. This is all the things that aren't captured inside of our model. When we're writing a formal model, we always have to assume that there's some error in the model that's explaining why reality is not matching up exactly with the model. Let's look at this graph on the left. I would say, so actually, the bad air model, miasma, is actually like a, unfortunately, pretty okay model for predicting disease, because bad things often carry germs, and getting rid of, or bad smelling things often carry germs, and getting rid of the things that smell bad prevents the germs from infecting people. So even without germ theory, the miasma theory produces this feedback loop where people are doing the thing that prevents the disease from being spread. So I would say this one on the left, this is like a really bad model. So maybe it's not miasma. Maybe this is the humors theory, or we're talking about how sinful a person is. So you say like, I don't know, I've been told that bad things happen to good people because they weren't actually good. They deserved it. So maybe we would say over here, this is a model of like, why did these people die? Because they were sinful. It has no predictive capabilities. But if we were to ask a primitive scientist who believed that sins caused cholera, why did this one data point happen over here? Why did this person die? That person might look back and say, yes, that person, they were very gluttonous. That's why they died. And if I pointed to another data point and I said, why did that person die? Sloth. Definitely that sin was the reason that they died. It has great predictive capabilities for the data that it already knows. But if I were to point to a new person and then say, what is the sin that will cause this person to die? They wouldn't be able to have any predictive power. This model is too retrospective and has no ability to predict things in the future. So this model on the far right, we call being overfit. And this is a danger that you can run into when you're doing machine learning, but there's nice tricks to avoid overfitting your model. This one in the middle, this Goldilocks model, it actually is never right. Like, it's never going to, this line and this point will never really intersect. But generally, it describes the data quite well. And we could expect, if I gave you some new data points, that they would still be described by this model in the middle. So our model is a lie that we tell ourselves that describes reality under certain circumstances pretty okay. I rewrote this model for the closure people in the room. I think it's beautiful. Some people don't. So, models. Data is good. More data is better. I'm going to switch away from 1850s London to talk more about actual machine learning in modern times right now. We still have the goal of trying to move the unknown things, this error term, into parameters of our model function. So my job right now, I work for a company that makes sensors for trains. And I'm building a piece of hardware that will collect the data out of the sensors, push it to the cloud, and then we can analyze this data. The primitives of my data, basically I have a GPS coordinate and a timestamp. And I'm trying to predict when will a train break, where is a train, when will a train be going through an intersection, things like this. Basically location and potential breakages. So to do this, we could say, I don't know, some of these parameters, I have my time and location, but maybe I also want to know something else that's not even in that data set that I'm getting. Maybe I want to know the weather. Perhaps the weather will influence where the trains will be at a certain time. If the rails get too hot because of the way that railroad tracks in Germany are welded together, if they get too hot, there's a chance that they'll rip apart and collapse and stuff. So trains have to go real slow when things are moving, when the weather is super hot. So looking at weather could help us predict something. So we want to add this parameter into our data set to help capture to help make a model that captures more information and makes better predictions. Maybe we have a data point that's actually too complicated. What I think of a good example for this is that I get my GPS coordinates, X, Y, Z, and I get a timestamp, the number of seconds that have happened since January 1st, 1970. But there's a lot of information encoded in a timestamp. Things that are relevant because we live in a society and we talk with other people and we have customs and norms. So a timestamp actually also tells us, with a little bit of sociology, whether it was a weekend, whether people were working that day, whether it was a holiday, whether it was peak hours, or whether nobody would want to be driving at this or riding at this time. Say it's 3 in the morning. So these sort of information can also help us understand and make predictions in our model. And then there's pieces of information that we can derive out of the data that we already have. So I'm given timestamp and GPS location. With this, I can identify whether a train is speeding up or moving or slowing down. So as a function of multiple records in my data set, I can create yet another column and add a column that says, or add another column that says acceleration and the rate of acceleration. So these are all things that I can do to help hint to my model what's going on in reality. So data is good. More data is better, unless it's not. And I hope you didn't just hear me drink. Sometimes the parameters that we give just aren't helpful. For example, this sinfulness or the amount of phlegm and blood, the balance of phlegm and blood that the person has in their body. These things probably don't have any predictive power in most models, but if we included that in our predictive function, it would just confuse the algorithm. Maybe it would make computational complexity go way up. So sometimes we just want to remove them. And there are tricks we can do, like dimensionality reduction or principal component analysis, that help us understand which things can we just throw out altogether. So I assert to you that the hard part of making a model useful is not choosing the model. It's not hyperparameterizing the model. It's not even getting the data for the model. More likely, it's like the case of Hamburg, where we have a perfect model. We know exactly what's causing the problems. We know exactly how to solve the problem. Maybe we won't always know exactly, but we'll have a good model. But there's going to be problems in our organization, problems in our systems, problems that are human problems that are preventing us from implementing the model that we have that would be good enough. And this will prevent us from being useful. As complicated as our computer systems are, it's always the people and the human systems that are more complicated. Projects fail not because the tech is too hard, but because people are hard. But here we are with a mature model. You've got your data all grown up, little baby. It's you. You're the scientist now. There's your model, trusty thing in your right hand, and you have this monkey on your shoulder. I should have been that monkey, thinking about the business, helping you remember, I actually have to care about the humans involved in this. Otherwise, I'm not being very useful. I'm just a dude with a sword and a wolf. I'm going to do more water. So remember that models are lies. They're useful lies, but they're always lies. Sometimes they're super not helpful too. You have lots of choices for all the different types of models you can use. You can do gradient descent, you can do genetic programming, you can do naive Bayes stuff, you can do convolutional neural networks. There's all sorts of different models you can swap in and swap out. There's different ways you can hyperparameterize them. But I suggest that these are not the hard decisions. The hard decisions are when we want to dig in and do awesome, badass science, that actually we just have to add a new feature that will make the user a little bit happier, will get retention up or something like that. A lot of times we have to make pragmatic decisions instead of drilling down more and more and more and being the perfect data model builder. We have to do the human stuff, which is, for a lot of us, a really hard pragmatic decision to make. We have to say, here I am, skilled at software, skilled at statistics, skilled at whatever, but I'm having to solve this age-old problem of getting people to work together to build something towards a common goal. So for me, I assert that that's a pretty hard but pragmatic decision to make. And while I'm talking about pragmatic decisions, I think it's impossible to have conversation about pragmatic decisions in data science without also talking about ethics in data science. We live in a world where the software that we build and the data science-y stuff that we do is physically changing the shape of our planet and permanently changing the shape of our societies. We have companies competing for who will make the most profit over war, for who can make the most profit deporting, imprisoning other people, displacing people. I think between surveillance capitalism, between the climate crisis before us, between war for profit, we have to look beyond this just, I'm not going to build the shitty software that destroys society and that destroys the planet. I think the pragmatic decision is that we work together, that we organize, that we do collective action to stop other people, actively stop other people from doing things that destroy the planet and destroy society. It's going to take solidarity, it's going to take a lot of hard work, it's going to take a lot of trust, it's going to take y'all and me together, but we can build another world, and I think we should go do it.